studied many gas laws such as Avogadro's law, Boyle's law and Charles' law, etc. And you know the ideal gas equation is PV is equal to nRT. So, the ideal gas equation is PV is equal to nRT. So, we can say if a gas obeys the gas laws or if it obeys this ideal gas equation, the gas is said to be ideal gas. If any gas deviate from these gas laws or it do not obey the gas law, or if PV is not equal to nRT for any gas, it is said to be a real gas. Usually, all the gases tends to behave as an ideal gas under certain conditions, but not under all conditions. It can act as an ideal gas only under certain conditions of temperature and pressure. Under not all conditions, it can act as ideal gas. So, the gases deviate from ideal behavior under certain conditions. So, the compressibility factor measures the deviation of real gases from ideal behavior. It is the measure of deviation of real gases from the ideal behavior. This is denoted by the letter Z, and mathematically it is given as Z is equal to PV by nRT. Here P is pressure of the gas, V volume of the gas, N number of moles, R is gas constant and T is the temperature of the gas. So, we can say the ratio of PV and nRT is the compressibility factor Z. Okay. This compressibility factor Z measures the deviation of real gases from the ideal behavior. To what extent it deviates is measured by this Z factor. Now, for an ideal gas, you know PV is equal to nRT. PV is equal to nRT means if you divide PV by nRT of an ideal gas, you will get the value of Z is equal to 1. Am I right? PV has the same value as that of nRT. So, the number is divided by the same number. So, the value will be equal to 1. So, for an ideal gas, Z is equal to 1 at all temperatures and pressures. All temperature and pressure, Z is equal to 1 for ideal gas. We can draw a plot for Z versus P for an ideal gas. Here P is taken in atmosphere, 0, 100, 200 atmosphere, 300 atmosphere, 400 and 500 atmosphere. And in this axis Z is taken. You know Z is PV by nRT. So, 0.5, 1.5 and 2. For ideal gas, Z is equal to 1. So, at any pressure may be 100 atmosphere, 200 atmosphere or 300 atmosphere. It does not matter whatever may be the pressure, but the value of Z is 1 for an ideal gas. So, you will get the line like this. This will be parallel to pressure axis, isn't it? It is parallel to pressure axis. This line is obtained for ideal gas. Under this area, Z is less than 1. See here, Z is less than 1. And above this ideal gas line, Z is greater than 1. Now, for an ideal gas, Z is equal to 1. So, you get a straight line like this, which is parallel to the pressure axis. Okay. When a gas will behave ideally, it should satisfy two conditions. What are the conditions? The volume occupied by the individual molecule should be negligible when compared with the total volume of the gas. See, if this is the container, it is the volume of gas. The volume occupied by individual molecule like this should be negligible when compared with this total volume. And another condition is that the attractive force between the molecules should be negligible. That means there should not be any attractive force between the molecules, gas molecules. So, volume of individual molecules should be negligible. Similarly, attractive force should be negligible for an ideal gas. When these conditions can be satisfied by a gas, under two conditions, these two can be achieved by a gas. What are the conditions? At low pressure and at high temperature. Under low pressure and under high temperature, a gas can behave as an ideal gas. What happens at low pressure? Imagine the pressure is very low, so the volume will be very high. So, comparing with this volume, the volume occupied by individual molecule is negligible, is it not? So, under low pressure, the first condition is satisfied by a gas. Pressure is very low, the volume is very high, total volume of the gas is very high. So, you can neglect the volume occupied by an individual molecule. At the same time, at low pressure, what about the density of gases? It will be very low. If density is very low, what will happen to the attractive force of the molecules? You know, if density is very low, the molecules will be far apart from each other. One molecule is far apart from another molecule, is it not? So, there cannot the existence of attractive force. Hence, the attractive force is negligible. So, this condition is also satisfied by a gas under low pressure. So, we can say any gas behaves as an ideal gas under low pressure. Let us see some examples here. If you draw the same plot for some gases like hydrogen, helium and some other gases, the lines will be like this. Hydrogen, at this area pressure is very low, that is 0 pressure, or 0 to 1, 2, 3 atmospheres like that. It obeys gas law, and then it shows a positive deviation like this. So, hydrogen at low pressure obeys gas law. At low pressure, it acts as an ideal gas. Is it not? At low pressure, gases tends to behave like ideal gas. Similarly, you get a line for helium like this. For nitrogen, at low pressure, it obeys ideal gas equation. So, the line starts here and then slightly it shows negative deviation. Here, if Z is equal to less than 1, it is called negative deviation. If Z is greater than 1, it is positive deviation. Nitrogen shows a negative deviation, then reaches the minimum like this, and then it moves toward the positive side. So, this line is obtained for nitrogen. For methane, the trend is similar to nitrogen, but little more deviation. It is for methane. Carbon dioxide shows more deviation than all gases. So, all these gases obeys gas law at low pressure region. When the pressure is increased, there is a deviation in its behavior. That is, at high pressures, this acts as a real gas. Right. Now, let us move to temperature. I told you, at high temperature, the gas behaves ideally. At high temperature, you know, the kinetic energy of the gas will be very more. Is it not? Okay. If kinetic energy is more, what happened to the molecules? They will move so fastly. Is it not? So, if a molecule moves faster, there cannot be any attractive force. So, again at high temperature, this condition is satisfied by a gas. So, at high temperature, the molecule tend to behave like ideal gas. Let us see this with an example of nitrogen. Here, as usual, we are taking Z, that is PV by nRT, and here it is pressure in atmosphere 0. You know already, for ideal gas, Z is equal to 1. It is 0 0.9, 0 0.8, 1.1, 1.2. These are the Z values. Here you can write the pressure value in atmosphere. Here, what we are going to plot is the Z versus P for nitrogen, Z versus P for nitrogen at different temperatures, You know, for ideal gas, Z value is equal to 1 like this. Nitrogen at the temperature of 220 Kelvin, the plot will be like this. It is at 220 Kelvin. Look here, at low pressure, it obeys gas law, then it shows negative deviation here, reaches some minimum and then moves towards the positive side. At somewhat higher temperature such as 273 Kelvin, the deviation is slightly less because the temperature is slightly higher, is it not? So, the line will be like this. Still at high temperature, say for example at 327 Kelvin, the nitrogen gas, which is a real gas actually, it obeys gas law to certain range of pressure and then show a positive deviation. Then at further higher temperature as 400 Kelvin, it shows a positive deviation. So, from this what can you understand? See, at low temperature the gas shows maximum deviation from the ideal line. This is the line of ideal gas, is it not? So, at further high temperature it shows lesser deviation, and then at this temperature over a range of pressure, say from 0 atmosphere to this much, in this range of pressure the gas obeys ideal gas laws, is it not? So, it acts as ideal gas at this temperature. This temperature where a real gas acts as an ideal gas over an appreciable range of pressure is said to be boil point or boil temperature. Boil temperature or boil point. What is boil temperature? The temperature at which the real gas acts as an ideal gas over the appreciable range of pressure. So, this is the boil temperature, and above the boil temperature the gas always shows the positive deviation only. Right. Now, you know, at low pressure the gas behaves as an ideal gas, At the same time, at high temperature, the gas behaves as an ideal gas. Right. What is the Z value for real gas? Z value for real gas. You know, Z is equal to PV by nRT. Since this is for a real gas, we can write the volume as V real. So, V real by nRT is equal to Z. Now, for ideal gas, PV is equal to nRT. This is V ideal, is it not? Okay. This is V real and this is V ideal. Now, V ideal is equal to what? It is equal to nRT by P. Rearrange this equation. V ideal is equal to nRT by P. Now, here what you have? P by nRT. It is nRT by P. You can substitute 1 by V ideal here, is it not? 1 by V ideal. So, the equation becomes Z is equal to V real by ideal, V ideal. So, compressibility factor of Z is equal to V real by V ideal. V real is the molar volume of real gas, whereas V ideal is the molar volume of the gas when it behaves ideally. So, by knowing the Z equation, V real by V ideal, similarly Z equal to PV by nRT for real ideal gases, by knowing these things, you can calculate the compressibility factor of any gas. Okay.